I've seen tweets from people saying they can't believe climate change science because water isn't said to be a greenhouse gas. So we're going to think about some aspects of water, including ice, and relate them to the greenhouse effect. In the video about CO2 as the green peril, I showed this plot of radiation that is emitted from the surface of the Earth. That is, in the infrared, the radiation felt as heat rather than seen by us as light. A motion of CO2 when the molecule bends occurs slap bang across the top of this emission, and this gives a mechanism for the absorption of the infrared, so warming the atmosphere. There are two other molecules that contribute very strongly to the absorption in this energy range. One is ozone, O3, which absorbs to the higher energy of CO2. And we'll look at that in another video. The water molecule can also bend, and so this is also a mechanism for absorption of the infrared. But this is at rather higher energy still, at which point the surface of the Earth emits lesser energy. However, the water molecule can also rotate, and this is a way for water molecules to absorb to a lower energy than CO2, but still in this critical regime. This is possible because of the lower symmetry of the water molecule. Unlike CO2, it is bent, and so it does not have a center of symmetry. We can see those two motions in this cartoon. Firstly, there is the bend, and then the rotation. And both of these contribute to the greenhouse effect. Greenhouse gases, so called, are those which hang around a long time and can mix thoroughly in the atmosphere. There's no great pool of liquid or solid, and that is exactly the opposite of water, where there is a vast amount of water both as liquid and solid, and we know from personal experience, the umbrella experience, that the lifetime of water molecules as vapour is much shorter, days, not years. As a result, the amount of water vapour in the atmosphere responds to the temperature changes which are created by the longer-lasting greenhouse gases. This graph shows the vapour density of water that can be held by air at different temperatures before it saturates. The units are in tons per cubic kilometre. At 10 degrees C, there can be about 10,000 tons in this volume. But there is an upwards curve, and by 35 degrees C, it is about 4 times larger. The warmer the atmosphere, the more water can be supported until it precipitates as rain or snow. Also, the atmosphere behaves then as a weightier blanket. A vital property of water is the way in which the molecules link together by intermolecular interactions called hydrogen bonds. They are in the liquid and the solid. In the vapour, the molecules predominantly are separate. This is a representation of 13 water molecules as a tiny cluster within liquid water. The red oxygen atoms link to 3 or 4 hydrogen atoms in the main, sharing with neighbouring molecules. In crystalline ice, the structure gives hexagonal-shaped channels. The result of this is that it takes a lot of energy for changes in phase to happen between ice and water and the vapour. Here's a demonstration of the energy needed to change phase, ice to water and liquid to vapour. I have about 330 mils of water in this measuring cylinder used for making bread. That represents the energy in megajoules that is needed to melt 1 kilogram of ice. And as it happens, if you heat 1 kilogram of water from 20 degrees C, room temperature, to boiling point, virtually the same energy is needed. Rather surprising, I think. The melting process occurs at a constant temperature, and it is evident that that heat needed is latent, and that reduces the potential temperature rise. The latent heat for vaporizing liquid water is nearly 7 times higher still, and that's represented by this jug, All the hydrogen bonds are broken in that process. Again, this process partly mitigates the temperature rise that the greenhouse effect might give. It also makes cooling trickier. But there are consequences for the increase in the greenhouse effect for water, for life, and therefore for us. Warming waters expand, and also there is more fresh water melting into the oceans. As this table shows, the loss of Greenland and Antarctic ice to liquid water would in time cause my town to be inundated and become off the shore of Salisbury by Sea. Lowering the density of sea off Greenland weakens the driver for the Gulf Stream, and thus will make our own climate more extreme. Unfreezing also releases gases like methane from sea and land, and it also makes the earth less reflective and more absorbing. This is bad news all round for the future, I'm afraid. This is just more evidence for the need to reduce our energy use and head to carbon zero with urgency. Next up, we look at another relatively short-lived atmospheric gas, ozone. Short-lived for quite a different reason.